Hello, in this video, let's look at the effect of mismatch on differential amplifiers. So in an ideal differential amplifier, as we've seen, both arms of the circuit are essentially identical to each other, which means that when the same voltage or the same signal is applied to the gate of the differential pair, both arms of the circuit swing in the same fashion. And therefore, what happens is that if I'm taking a differential output between the two arms, then if the input signal is the same to both the input transistors or differential pair, the output differential voltage is a zero. However, in reality, circuits are manufactured, so there exists a variation, there exists mismatch between various circuit components. And therefore, what happens because of this mismatch, it's very hard to create two circuits which have completely matched components. What we can try and do is ensure that the probability of them being matched or the mismatch is as low as possible. So there are techniques to do that, but you essentially cannot do away with mismatch. Now, because of that mismatch, therefore, even in differential mode, an output voltage can appear at the differential output even when the input signal is the same or when the same input signal is applied to differential pair, right? So this is something which is unwanted. So we'll basically look at how this common mode signal comes about. So this is known as the common mode gain, and what are the circuit parameters that impact this common mode gain. So let's look at mismatch in a couple of ways. So the first way we look at mismatch is let's assume that we consider this ideal differential amplifier. So again, the inputs are V1 and V2. M1, M2 form the differential pair. ISS is the tail current. The difference in the circuit here is that the two load resistors are not equal. One arm has a load resistance of RD, the other arm has a slightly different load resistance of, say, some RD plus delta RD. Now, when I think about a common mode small signal, that is when I apply a small signal that is same at both the inputs of the differential pair, and in small signal, basically my tail current source becomes an open circuit. So this node X in small signal is open circuited. So what happens in that case is that even though there's a mismatch in the arms, because this node is essentially movable, this mismatch doesn't cause an output voltage to appear between the two arms because Vx moves in such a way that the difference in the two voltages becomes a zero. Right? And that's because this Vx can move. There's nothing holding Vx or pinning Vx down because Vx is connected only to a ideal current source. Now, therefore, in such a case, even though there is a mismatch in the two arms of the differential amplifier, there is no differential voltage when the same voltage is applied at both V1 and V2. Right? Now let's look at what happens. Suppose instead of having an ideal current source, I had a non-ideal current source as the tail current. In which case, what do I mean by non-ideal current source? It means that this current source doesn't have an infinite impedance. It has some finite impedance. So let's assume that that impedance is some RSS. Right, so this is now your differential pair, right? The two arms again are RD and RD plus delta RD. I have two outputs, VO1 and VO2, and I'm looking at the common mode operation. That's I'm looking at the operation when I apply the same signal to both the gates of the differential pair, right? Again, for analysis sake, let's assume that lambdas are zero. So let's assume that we have applied an input signal of VICM, where CM stands for the common mode, to both the gate terminals. Let's assume that both the transistors are identical, so there's no difference between M1 and M2. And let's also assume that delta RD is very small. And when I assume that, then I can make a very simplifying assumption that even though there's a small delta between these two, the difference in the bias currents of M1 and M2 is not a lot. So I can still assume that the bias currents are ISS by 2, which means that the transconductance of M1 and M2 are assumed to be equal. Now, if I look at the gain from this VICM input, that is the gate of M1 to the drain of M1, the gate of M1 to the drain of M1, so this is going to be a common source amplifier. However, the source is not grounded, but the source has an RSS connected to it. So this is going to be a common source with source degradation. Now the difference between this and the regular source degradation transistor is that the bias current of M1, right, is I by 2, whereas the current flowing in RSS is the tail current or I. Which means that RSS, if I were to use it for source degradation of M1, I need to consider twice the RSS because the current flowing in M1 is half that of the actual current flowing in RSS. Right? So therefore, if I write the gain from VICM to VO1 or V1 to VO1, V1 to VO1 can be written as GM RD, that is the GM of M1 times RD divided by 1 plus GM into 2 RSS. 2 RSS again because the current in RSS is actually twice that of what's flowing in M1. Or in other words, my VO1 to VICM is going to be minus GMRD by 1 plus 2 GM RSS. Now let's use the same logic and apply it to the other arm of the differential amplifier. So again here, if I now take the gain from V2 to VO2, from V2 to VO2 I have the gain as GM into RD plus delta RD. Now here, because the drain resistance is not RD but some RD corrupted with some delta RD, divided by 1 plus 2 GM RSS. Again here, because the current flowing in M2 is half that of the current flowing in RSS. So which means that my gain from V2 to VO2 is minus GM into RD plus delta RD by 1 plus 2 GM RSS. So what you see here is that even though the input signals are VICM to both the gates, VO1 and VO2 are not equal because VO1 and VO2 are connected to AC ground through different load transistors. One is connected through RD and one is connected through RD plus delta RD, right? So therefore what happens is that because VO1 and VO2 are not identical, a differential output voltage develops. So if I'm going to measure the voltage between these two terminals, there is going to be a finite voltage developed even though the same input is given to both M1 and M2, and this differential output voltage is given by minus GM into delta RD by 1 plus 2 GM RSS. And what you see here is that this differential voltage, right, is dependent on the deltas between the load resistors. So the higher the load resistance differences, the higher the output voltage you're going to see. Again, remember, this is a non-ideal condition because there is no differential input signal. Even though there is no differential input signal, I am seeing a differential output. So this is kind of an unwanted signal, if you will, in a differential amplifier. Now let's look at what happens to the differential gain. So again, here in differential gain, if I assume that my delta RD is very small, then I can treat this circuit as very similar to a standard ideal differential pair, in which case my V0 by VID is going to be minus GMRD. Right? And here what we're doing is we're saying that this value of delta RD is very small and therefore I can think of the differential mode as directly similar to that of the ideal differential amplifier. Right? So a little bit about the figure of merit. So let's think about an amplifier. An amplifier, a differential amplifier to be specific, has two inputs V1 and V2 and an output Vout. So I talk about a differential gain for the differential amplifier and a common mode gain for the amplifier. What is common mode gain? If I short V1 and V2 and I measure Vout by this shorted voltage, the gain between those two is going to be the common mode signal. To find the differential mode gain, I will apply a differential voltage between V1 and V2 and measure Vout. The ratio of the differential input to the differential output is the differential gain of the amplifier. So if you look at any generic differential amplifier, if I had two signals V1 and V2 applied, then the common mode signal can be thought of as the average of the two signals. Right? So this is going to be our input common mode voltage as V1 plus V2 by 2. The differential mode in this case is going to be V1 minus V2. And so if you know the differential gain and the common mode gain, then you can write the output voltage as the common mode gain times the common mode voltage plus the differential gain times the differential voltage, which in other words can be written as Vout as ACM into V1 plus V2 by 2 plus AD into V1 minus V2. And so what do you want? So in an ideal differential amplifier, you want this differential amplifier to highlight the difference in the two signals, right? You want it to pinpoint the difference. And sensitive differential amplifier wants to ensure that even a small few millivolt signal between the two signals is amplified, and you want to effectively play down the commonality between the two. So we define what is known as a common mode rejection ratio. This is a figure of merit of the differential amplifier and is defined by the ratio of the differential gain to the common mode gain. Right? So in an ideal differential amplifier, you want this to be infinite. That is, you want a finite differential gain, but you want a common mode gain which is essentially close to zero. So AD wants to be as high as possible, ACM wants to be as low as possible. So a good differential amplifier would be one with a high CMRR. Typically, this is expressed in decibels, or in other words, to calculate CMRR, I would write it as 20 log of mod AD by ACM. Now let's go back to the circuit which had the difference in the load resistances. And so if I talk about the common mode gain, the common mode gain is V0 by VICM, it's minus GMRD by 1 plus 2 GM RSS. So again, you see here that the common mode gain is proportional to the difference in the circuits, if you will. If that delta RD was zero, then essentially you wouldn't have had any common mode gain to begin with. So the common mode gain is showing up because of the fact that you have this mismatch in the circuits. The differential mode gain is given by minus GMRD, and so in this case I can talk about CMRR as the ratio of differential gain to the common mode gain, which is GMRD by GM delta RD into 1 plus 2 GM RSS. Or in other words, the CMRR is given by 1 plus 2 times GM into RSS. Now this RSS is the impedance of the tail current source divided by the relative mismatch in the load resistances. So you see something which is expected is that as you make the current source more and more ideal, you're going to get a better CMRR. So if you want a good differential amplifier, you want to ensure that this RSS is as high as possible. And the second thing you want to do is that you want to reduce the mismatch as you can. The higher the mismatch, the lower the CMRR. Now let's look at another cause of mismatch when the transistors actually are mismatched, and this can happen either due to a difference in the gate oxide thickness, due to difference in VT which comes out because of different dopings, due to a difference in W's, due to difference in L's, work functions, etc. Right? So there are multiple reasons due to which M1 and M2 needn't be perfectly matched to each other. So we look at a very generic case where M1 and N2 are so distinct that they support a different bias current and hence a different GM. Right? So let's assume that I have a generic differential amplifier. Assume the transistors are in saturation. V1 is the voltage I've applied to the gate of M1. V2 is the voltage I've applied to gate of M2. I have a non-ideal current source RSS. And I have a load resistance which is nominally equal to each other. And again, I'm talking about a differential output, so I have a VO1 and a VO2. Now again, if I want to find the VO, what I'm going to do is the strategy I'm going to apply is I'm going to try and use the principle of superposition to relate VO1 to V1 and V2. Similarly, VO2 to V1 and V2, and then I'll talk about the differential output voltage as VO1 minus VO2. Now if I look from V1 to VO1, V1 to VO1, we've done this a couple of times before, is a common source amplifier with source degradation. And what's the source degradation? It's given by this RSS times and the input resistance of this common gate amplifier. Remember, V2 is going to be grounded in this case. So the net source rate degradation is given by RSS parallel 1 by GM2. So therefore VO1 to V1 can be written as minus GM1RD divided by 1 plus GM1 into RSS parallel 1 by GM2. And you collect the terms, you get this as minus GM1RD into 1 plus GM2 RSS divided by 1 plus GM1 plus GM2 into RSS. Right? So this is the gain from 1 to O1 when V2 is not present. Now if I look at the gain from V1 to VO2, V1 to VO2 basically goes through a source follower which is made up of M1 to this output node here, and then a common gate from this through M2 to output, right? So from V1 to VO2, I'm going to look at it as a cascade of a source follower with a common gate configuration. And so again, if I want to find the gain of this circuit, if I call this intermediate node X, Vx to V1 is the source follower gain of M1, which is GM1 into RSS divided by 1 plus GM1 RSS. And the output resistance, again, why is the output resistance important? Because I'm looking, the second stage is a common gate stage. The common gate stage, the input comes in at the source, so you need to worry about it has a finite Rn. Rn is not infinity. So therefore you need to find out what R out is, what Rn is. Only a portion of this output voltage is going to fall at the input of the common gate. So the R out is given by RSS parallel 1 by GM1. VO2 to Vx. VO2 to Vx is nothing but GM2RD, again because lambda is 0. And here the Rn of this common gate is 1 by GM2. So therefore R out of the common source is, of the source follower is this. Rn of the common gate is this. So therefore if I want to write VO2 by V1, it is GM2RD, which is the gain of the common gate, times the gain of the source follower, times the resistive division between the input and the output of this cascade, which is 1 by GM2 by 1 by GM2 plus RSS parallel 1 by GM1. And again, when you collect these terms, you're going to get this as VO2 by V1 is GM1 GM2 RD RSS divided by 1 plus GM1 plus GM2 into RSS. Right, so we have established VO1 to V1, VO2 to V1. So these are the gains, respective gains from gate voltage 1 to the output 1, gate voltage 1 to the output 2. We know this is a symmetric circuit, so I can use laws of symmetry and basically write the gains from V2 to VO1 and V2 to VO2, which in this case would be the cross versions of this, right? So this would be VO1 by VO2 would be GM2 GM1 RD RSS by 1 plus GM2 plus GM1 RSS, and VO2 by V2 will be the common source with source degradation, which would be given as GM2 RD into 1 plus GM1 RSS by this. So basically now I've established the relationships between the two output voltages with the input voltages. And so therefore if I want to talk about the differential output voltage, the differential output voltage is given by VO1 minus VO2. And so all I need to do is sum up the two relationships. So what I get is the differential voltage is given by minus GM1 RD into 1 plus 2 GM2 RSS divided by 1 plus GM1 plus GM2 RSS times V1 plus GM2 RD into 1 plus 2 GM1 RSS divided by 1 plus GM1 plus GM2 RSS times V2. So it's sum A times V1 plus B times V2. So you see that the differential voltage is a linear function of V1 and V2. Now let's now use this to find out the common mode gain and the differential mode gain. So when I want to find the common mode gain, I assume that this V1 and V2 are identical and both of them have been given the signal which is the common mode signal. So in this expression for V out, I substitute V1 and V2 to be VICM, in which case I get my V out as this, and I collect the like terms, and then I can find out my common mode gain, which is V0 by VICM as minus GM1 minus GM2 into RD by 1 plus GM1 plus GM2. So again, you're curious, the common mode gain arises because there is a delta of the two transistors, right? In the ideal case, when GMs of both the transistors are equal, you're not going to get a common mode gain. So this whole common mode gain is coming about because of the mismatch in the two parts of the differential amplifier. And larger the mismatch, the higher the common mode gain. Now in differential mode, again, since I already know how this works, in differential mode, all I need to do is apply V1 equal to minus V2 is equal to VID by 2. In other words, V1 is VID by 2, V2 is minus VID by 2. And again, if I substitute that and collect the terms, I get my differential gain as VO by VID, which is minus of GM1 plus GM2 into RD plus 4 GM1 GM2 RD RSS divided by 2 into 1 plus GM1 plus GM2 into RSS. So now if I want to talk about the common mode rejection ratio of the circuit, I know the differential gain in terms of GM1 and GM2. I know the common mode gain in terms of GM1 and GM2. And so the CMRR is given by the ratio of the differential gain to the common mode gain. And what I get it as GM1 plus GM2 plus 4 GM1 GM2 into RSS by 2 by GM1 minus GM2. So again, I'll draw your attention to two terms here. CMRR is inversely proportional to GM1 minus GM2. Right? Now this is the mismatch. So larger the mismatch between the transistors, smaller the CMRR. And second thing you see here is CMRR is directly proportional to RSS. RSS is the impedance of the tail current source. So the higher I make the impedance of the tail current source, or as I make the tail current source ideal, I'm going to end up getting a high CMRR. So again, the learning is very similar to what you saw in the resistance mismatch, right? In that to improve CMRR, you want to make the current source as ideal as possible, and you want to reduce the mismatch as you can. So in analog design, there are a lot of tricks designers use so as to ensure that these two transistors are laid out in such a way that they'll be as close as possible to each other. Now the CMRR, if I assume there is a small delta between GM1 and GM2, so one can be treated as GM plus delta GM by 2, one can be treated as a GM minus delta GM by 2, then I get my CMRR as GM by delta GM into 1 plus 2 GM RSS. Again, this is very similar to the RD expression we got, right? So again, the concept is the same. The CMRR comes about because of a mismatch. So you want to keep the mismatch minimum if you want to have a good CMRR. And second thing is you want to keep your tail source current as ideal as possible. And so to first order, if I assume that this GM RSS is much larger than 1, I can approximate this as GM squared RSS by delta GM. So the mismatch in circuit components causes non-idealities in a differential amplifier. Common mode signal is a problem and can corrupt the output signal. So a common mode signal when present, right? If you have a finite common mode gain, then this common mode is going to corrupt your differential output, right? And that is something you don't want the differential amplifier to do. And this is measured by what is known as CMRR, which is a figure of merit of the differential amplifier. CMRR stands for common mode rejection ratio. And you want to design a circuit for a high CMRR. Typically that involves designing a circuit where you lay out circuit in such a way, or you design the circuit in such a way so as to reduce the mismatch between the various components and try and use a tail current source which is as ideal as possible.